When you turn the steering wheel of a passenger car, it feels like a direct one-to-one mechanical connection. You pull left, and the wheels point left. This data plot illustrates why that immediate reaction is an illusion. The relationship between your hands and the car's change in direction is entirely nonlinear. There is a specific sequence of events: the turns of the steering wheel, the alteration of the steer angle at the front wheels, the development of lateral tire forces, and finally, the actual alteration of the driving direction. This functional gap happens because chassis components are not perfectly rigid. They have elastic compliance. When you turn the wheel, you are twisting metal and compressing rubber. The vehicle resists immediate directional changes until those forces overcome the elasticity and generate enough grip to pull the mass of the car into a turn. To manage this physical delay, a driver relies on a constant stream of sensory data. We monitor the body's roll inclination, the feeling of transverse acceleration, and the self-centering steering torque. The job of the modern steering system is to bridge this gap. It converts the steering wheel angle into precise wheel positions, while simultaneously transmitting accurate feedback about the forces acting on the tire contact patches. Steering is an ongoing, real-time negotiation between human intent and the massive transverse forces pulling at the tires. Long before it handles dynamic cornering forces, the steering system executes a more vital job. Moving down the steering column, the engineering priority shifts from directional output to passive driver protection. In a head-on collision, a solid, unbroken steering column becomes a deadly weapon. It acts as a rigid structural member, transferring the kinetic energy of the crash directly into the passenger cabin. To prevent this, engineers utilize a telescopic collapsible steering tube. Instead of a single solid rod, the column is split into two sections, designed to act as a physical crumple zone and absorb the impact energy. The inner and outer tubes are connected by internal plastic bushes. These bushes shear under precise, calculated loads. Once they break, a flattened inner tube slides smoothly inside the hollow outer part. The steering column's most sophisticated design feature is its carefully orchestrated ability to self-destruct to ensure passenger safety. This technical layout reaches the EPS module, showing the intersection where mechanical rotation is converted into digital logic. Inside this assembly sits a micro-torsion bar. When you turn the steering wheel, this bar physically twists under the torque applied by your hands. As the spindle rises, that twisting motion forces a sliding sleeve to move axially along the grooved section of the steering tube. A rotary potentiometer detects this exact axial movement. It instantly translates the physical shift into a stream of data packets, sending them to the vehicle's electronic control unit. The system responds by activating a brushless servo motor. Driving a plastic worm gear, the motor injects high torque assist tailored exactly to the driver's input. Modern Power Assist operates as a reactive digital loop. The driver provides the initial signal, and the mechatronic system provides the physical strength. This technical drawing shows the historical baseline for steering, the recirculating ball gear. It used an input screw shaft where ball bearings ran through a thread to carry a steering nut, which then meshed with a toothed segment. This architecture required a network of pitman arms, intermediate rods, and ether arms. It is a bulky configuration, making it difficult to package in the tight engine bays of modern front-wheel drive cars. This cross-section details the modern solution, the rack and pinion system. Its design is simplified. A pinion gear driven by the steering column meshes directly with a lateral toothed steering rack. To ensure an immediate response, a guide bearing pressed by a coil spring keeps the rack continuously engaged with the pinion. This eliminates internal play and provides the driver with clear feedback from the road. By stripping away the intermediate linkages and driving the rack directly, engineers increased both the durability and the mechanical precision of the steering system. Looking at the front axle assembly, the straight-line lateral shift moves from the rack out to the tie rods. Here, two-dimensional force resolves into complex three-dimensional rotational geometry at the wheel hub. Steering rotation occurs around an inclined axis known as kingpin inclination. By angling the steering axis inward, engineers stabilize the wheel and generate the self-centering forces the driver feels in the steering wheel. This geometric diagram shows how the spatial positioning of the inner and outer tie rod joints must align with the vehicle's virtual center of rotation P to ensure stable handling as the suspension travels. Every component in this linkage is a physical manifestation of a precise three-dimensional geometric calculation designed to optimize tire grip. When a car enters a curve, the tire on the inside of the bend has a shorter distance to travel than the tire on the outside. To avoid tire scrub, the inner wheel must turn at a sharper angle than the outer one. This top-down schematic illustrates the solution, the Ackermann principle. The geometry is configured so that the wheels track different circular radii based on their relative distance from the turn's center point. This schematic highlights the steering arm angle, represented by lambda. The specific incline of the arms mechanically forces this difference angle, allowing both tires to roll smoothly through their respective arcs. Torque travels from the driver's hands, passes safely through the collapsible column, is multiplied by the mechatronic brain, and resolves into the precise three-dimensional geometry of the tires. Modern steering has evolved beyond a simple mechanical rod into an integrated system that conquers physics in milliseconds.